Okay, so let's start with an overview of multiplying. Multiplying in binary is the same as multiplying in base 10. What we're going to do is we're going to turn this into an algorithm right here that we can implement in hardware, not in software. So then we're going to visualize this in hardware right here. And then the orchestrator, the one that's pulling all the strings of all these other various circuits, is going to be this algorithmic state machine right here. And we're going to develop a diagram of it. I'm going to try to develop this algorithm by hand. And what I want to do is call these right here partial products. I'll call them PPs for short, partial products. So we're going to start off with a 0, 0, 0, 0. Let's call this init. And then we're going to write down our first partial product, which is 1 times this. So we're going to write down our first partial product. First partial product. Okay, and then we're going to add. So we get a 0, 1, 0, 1. Add. And then we're going to shift. So just like we shift this way, we're going to shift, instead of shifting left, we're going to shift right. All right. And now we're going to write down our second partial product. Our second partial product is 0 times this, so it's a bunch of zeros. 0, 0, 0, 0. Then we're going to add. Now that 0 comes from the carry, right? So it comes from the carry of these two. Carry. There wasn't any carry. So we're adding this plus this, that's a 1. This plus this is a 0. This plus this is a 1. This plus this is a 0. Okay. So this is our second partial product. This is our shift. This is our add. All right, so this is our second add. And remember, we have that 0 coming down. And now we're going to shift again. So this 0 moves over. That 1 takes its place. Then I have a 0, 1, 0. Now, did I get any carry? No, there's no carry. Right? The carry would have come from up here. This no carry. All right. Then I go and I write down my third partial product, which is right here. 1, 0, 1, 0. And now I add. So this 0 plus that 0 is 0. 1 plus 1 is 0. Carry the 1. 0 plus 1 is 1, and there's no carry. So this is my third add. All right. Now I'm going to shift. So you can see a pattern's developing. All right. So I'm going to get a, that 0 moves over. 0, 1, and that 0 moves to right here. That 0 moves to right here, and 1, 1. All right, and there was no carry. All right, shift. And now I'm going to write down my third partial product, which is a 1, 0, 1, 0. And now I'm going to add. So that 0 plus that 0 is 0. 1 plus 1 is 0. Carry the 1. 1 plus 1 is 10. Carry the 1. 1 plus 1 is 10. And then there's a carry. Wow. Okay, so that was my add. And now I'm going to shift. So that 0 moves over, that 1 moves over, that 0 moves over, that 0 moves to here. And then I have this 0. This 0 moves over. That 0 moves over. That 1 moves over. And that's my answer. So what are my operations? I have, let's see, I have initialize, first partial product, add, shift. Partial product, add, shift. This was a partial product 2. This was a partial product 2. Add, shift. So init, partial product, add, shift, partial product, add, shift, partial product, add, shift, partial product, add, shift. Okay, so let's try to figure out the hardware we're going to need. It looks like I have a 4-bit shift register right here. Another 4-bit shift register right here. And I have a flip-flop out here for this stuff. For the carries. Remember, this last one carried into here. So this is a flip-flop. This is a shift register. This is a shift register. Then I need some kind of adder. And then these partial products, I need to figure out how to add them. Let's see, the partial product was either this or a 0. So I bet I could just hook up this multiplicand in here. This number would go into here. So this is another kind of a it's not going to be a shift register, it's just going to be storage, permanent storage. Let's call this just call it a register. So this is going to carry the 1010 in it. And then this adder is going to have this, let's call this A. So there's going to be some kind of register right here, shift register A, that's going into here, and it's adding these, and they're coming out. And then this shift register B would be right here, shift register B, and we would be shifting from this one into this one, right? That's this 0 popping out here, and then this 10 popping out, and then this popping out. All right. And this adder is going to go into here, right? The result that's adding, and then there's going to be the result of adding is also going to influence this flip-flop right here. So the adder is going to influence both of these. So I want to figure out the role of this multiplier right here. The multiplier determines whether we add, the multiplier determines what this partial product is. So if we put this in here, 1, 1, 0, 1, then the first partial product is based upon this 1 right here. 1, 1, 0, 1. So this 1 determines the value of that partial product. In a sense, this 1 says add. And then when we shift, that 1's gone, and this one determines our next partial product. This 0 right here determines that partial product. So it's influencing this. This is going to influence this, and it's going to influence, this is just after the shift, so we still have a 1, 1, 0 right here, right? It's going to influence this, and whether we're going to add. And basically it means don't add. Right? Because this, adding to 0 is basically the same thing. It's the don't add. All right, and then when we shift, we get a 1, 1. So now we have a 1, 1 right here. The 1, 1 determines this 1, now determines that partial fraction, and then it says add. And then we shift, we have just this 1 left. This 1 determines and says add, and then when we do a final shift, all the green is gone. So this register serves two purposes. The first purpose is to hold the multiplier, and then the second purpose is to hold the extended answer, because our answer is going to be 8 bits. Wow. Okay, so let's try to get this adding concept in this hardware version of the circuit. This is the number we want to add or not add. So if we put it in here, that's what we did up here. If we put it in here, 1, 1, 0, 1, this rightmost bit is going to determine whether we add or not. Right? Right here, we don't add. Right? If it's a 0, right? If this is a 0, we didn't add. Now the adder is continuously adding. Constantly adding. Whatever's in here is added to here, and the result is put here. Now the result is 5 bits. 4 bits goes up here, and 1 bit goes up here, but the result only goes up here if we're adding. So this is happening constantly without a clock. This is a combinatory circuit. And it's creating a result, whether this is looking at the result and this flip-flop's looking at the result or not. Okay, so let's look at a more detailed version of this. You can see the two registers, you can see the flip-flop, you can see the parallel adder, you can see this rightmost bit. It's the algorithmic state machine that controls whether we shift right or not. So we're getting into the role of the algorithmic state machine, trying to tie all these pieces together. These shift registers and the flip-flop. Here you can see this register's input into the adder, so it's constantly adding. And this sum only goes into this register when this add line is hit by the algorithmic state machine. So the algorithmic state machine pays attention to this rightmost bit, and then if it's a 1, then it says add. Now there's 4 steps. Remember, there are 4 steps right here, 4 shifts. So we need a counter right here that can count up to 4 or count down from 4. Looks like it's counting down from 4, it's decrementing this counter. So the algorithmic state machine is going to decrement this counter. It's going to increment it to starting off at 4 or 3. And the algorithmic state machine is going to say complete when it's counted down 4 times, when it's shifted 4 times. Alright, so we're going to try to talk this through by hand. We're going to start off with going through here, S is 0. So the start bit coming from somewhere else is 0. And this algorithmic state machine is idling, doing nothing. Nobody's told it to do anything. It's just waiting to be started. A start bit comes in and it initializes, the very first thing. So it's going to initialize this counter at 4. So the initialization is coming out right here. It's coming into this circuit. It's coming in here to this register. So it's sticking in the multiplicand, which is 1, 0, 1, 0. It's initializing this register with 1, 0, 1, 1. It's initializing this register with a 0, 0, 0, 0. It's initializing this register with a 0. And immediately this parallel adder is adding 0 plus this, so it's adding 0, 1, 0. And there's no carry at this point. So we finished the initialization. Now we're at state 2, the algorithmic state machine 2. It says decrement. So the decrement line comes out, hits this counter, changes that 4 to a 3. Then it looks at M1. M1's value is a 1. M1 is an input right here. And because it's a 1, the algorithmic state machine says add. So the add line has a 1 coming out. That 1 comes in here and it says add. So it copies this 1010 up here. 1010. That's gone. And it copies this 0 up to here. And then it goes down here to state 3. So we're here at state 3, and our first command coming in is shift right. So the algorithmic state machine is sending out a command here saying shift right. Shift right starts right here and hits this flip-flop, hits this register, and hits this register. So we'll work our way backwards. This 1 disappears. That 0 climbs in here. That 1 moves over. That 1 moves over. That 0, this 0 moves over to here. And these 1s and 0s move over, and that 0 moves into here. And then this 0 moves into the flip-flop. So this flip-flop's value is still 0. Then we look at Z. Z's currently 0 right now because the counter's value is 3. And because Z is 0, then we move back up here to state 2. Now the minute this shift occurred right here, and we shifted over, and these values changed, that 1 plus that 0 adds up to 1. That 0 plus that 1 adds up to 1. That 1 plus that 0 adds up to 1. That 0 plus that 1 adds up to 1, and we have a carry of 0. Alright, so we're here at state 2 and we're decrementing. And then we're looking at M1. M1's value right now is 0. M1 coming in here is 0, so we're not going to add. We're not going to copy this blue 0 up there and these blue 1s up here. We're going to leave things alone. So because M1 is a 0, we're going to go straight down here to state 3. Okay, so we're down here at state 3 and we're shifting right. And we've got this 0 moving in there, so it stays a 0. Immediately, this adder is going to start adding again, and it's going to add 0 plus 0 is 0. Z is still 0. We have a value now of 2 right here, but the output is still 0. So we go back up here to decrement again. Decrement comes out, hits this. That's now a 1. We're done. We look at M1. M1's value now is a 1. 1 comes in right here and means add. Add hits here, and what we do is we copy this purple 0 right here over to here, and we load 1100 into here. And the minute that happens, then this number right here changes, but it's not being looked at. So we go down here to state 3. State 3 says shift right. So that's gone. This is gone. And our adder is now adding. It adds continuously, so 0 plus 0 is 0. So that's what's ready to be added. So that's what's the result of our shift right. Now we look at Z. Z's value is 1, so we still are outputting a 0. So we're still going to go out right here and hit decrement again. Okay, so we're at state 2 and we're decrementing. Decrementing comes out of the algorithmic state machine, comes into the counter, changes that to a 0. And then we look at M1. M1 is still a 1, so we add. Add means we copy all these 4 zeros up here. And we copy this 1 over to here. So our flip-flop value is 1 for the first time. Now we're done with adding. So we're down here at state 3, shift right. And that 1 moves in right here. And then we get a 0 moving in. Now we look at Z. Z looks up here and goes, wow, we're at 0, we're done, 1. So it goes complete and it stops. And we've got our answer. Our answer is right here. Yeah, it's the same answer as right here.